Finally, we have combustion reactions. So just a few more, hang in there. You'll be fine. Burning hydrocarbons. You guys should be fairly familiar with this one. Red, C3H8. That's carbon and hydrogen together. We could call that a tricarbon octahydride, right? But you usually call that propane. So we're just going to call that propane here. Propane gas, you might use it at your house if you live in the country for your heat and everything else. Whereas in town, you might have a propane tank for your grill, right? So everybody's familiar with propane, right? But when propane burns, when you react it with oxygen, a combustion reaction, you always have oxygen, but you also release a large amount of energy at the end of this, right? That's the point of combusting that propane, was to release some heat that you could cook your food with and or heat your house with, right? So I'm going to have a reaction here, and it's fairly simple to predict the products. All you do is mix oxygen with your two ingredients in that propane. So if I mix carbon with a little bit of oxygen, I can make a stable compound that you've heard of, carbon dioxide, right? If I mix hydrogen with a little bit of oxygen, I can also make another stable compound, which we just talked about, water. So those are going to be my two products, and those are my products every time, right? That doesn't actually change. As long as I have a hydrocarbon, as long as I have something like propane that has multiple carbons, multiple hydrogens, right? I'm going to make carbon dioxide and water. The only thing that's going to change is how this balances overall, and that's the toughest part of this reaction. I'm going to have to walk you through that real quick, make sure we can balance this. So I'm going to go through, and I have 3 carbons, 8 hydrogens. I would suggest if you're doing this kind of reaction, if you have a hydrocarbon, always do the water first. I'm going to show you why, right? Because since I have 8 hydrogens there, I should need 4 waters on the right. And because I have 3 carbons on the left, I'm going to need 3 carbon dioxides on the right. But I'm looking for that number in front of the water, because in this case, it's not going to be a problem. But when you were doing your balancing equations, you should have had examples like this. If that is an odd number in front of your water, that's your indicator that you're going to need to double everything, right? So be looking out for that, right? So if you have an odd number of waters, if I started out by having to put a 3 there or a 5, then I would know that I need to double everything to make this balance. Because no matter what, I'm going to have an even number of oxygens on the left side of this equation, right? So right now, 3 times 2, I have 6 oxygens in this carbon dioxide, and 4 times 1, I have 4 oxygens in the waters, in the water molecules. That's 10 oxygens total, right? But if there was an odd number of waters, then I'd have an odd number of oxygens. And in order to get this to balance, I need to multiply over here by a whole number. And 5 times 2 is even, right? 4 times 2 is still going to be even. 6 times 2 is going to be even. No matter what, you're going to have an even number of oxygens on the left, which is why you can't have an odd number of waters on the right. So this is balanced currently. Again, 6 plus 4 gives me my 10 divided by 2. I need to multiply by 5 on the left. But sometimes you'll have to double this, and you should have learned how to do that in the 3rd game in that balancing equation simulator. So again, I'm telling you what to look out for. Look out for an odd number of waters. So always do the water first. Otherwise, you should be able to come up with products and balance it appropriately. But finally, this is a combustion reaction. There better be a bunch of energy that comes out too. Right? So I want you to think about that as well. That's what makes this different than other kinds of reactions. But otherwise, burning hydrogen gas would be similar. But now I don't have carbon, so I only make one product. And that product is obviously going to be a water this time. But again, balance it appropriately. Since I have one water, right, this really isn't going to work. Again, again, I'd have to double everything, right? But otherwise, you might not have started with the hydrogen because 2 to 2, my oxygen tells me I should double this anyway, right? So 2 and 2, now we're good to go. But it's the same idea. It's the same thing as that last one. You just might do it differently. In the hydrocarbon example, you would have never started by balancing oxygens first because there's oxygen in 3 different things. Whereas in this reaction, you might balance the oxygen first and it would get you there quicker, right? But burning hydrogen gas, also a combustion, that's why my water rockets work. So again, I can make that hydrogen gas and I can burn it. It's very flammable, right? And it also burns very clean, as you notice, right? When you burn hydrogen gas, the only byproduct is water, which we love water. Living things love water. This could actually solve a lot of pollution problems if we add hydrogen as a fuel. But again, hydrogen is very flammable, right? You can't store it easily without explosive possibilities taking place. So, I mean, some of you have probably heard of the Hindenburg and what happened there. So, it's a good idea to burn it, but it's hard to store it safely. So, kind of depends on the context. Other examples, one I did in the demo, I burned that magnesium strip, if you remember, right? And when I burned that magnesium, again, all of these would require a little bit of spark, a little bit of heat. I had to put it in the flame in the Bunsen burner. But once it started, it got going and it reacted very vigorously, right? You remember there was bright white light that was emitted by that, right? In fact, it was blindingly bright. It doesn't seem that way on the video, but I couldn't look at it directly in the room, right? It would have blinded me. It was so bright. So that's a reaction we use frequently for a purpose, right? How do you think they make those bright and colorful fireworks, right? Magnesium, when it burns, creates this brilliant white light, and other elements that you sprinkle in there can change the color of that light. So a lot of reactions going on that you see on a day-to-day basis, but we don't always know what's actually occurring there. That's what you're learning about chemistry for. So you can actually describe what's happening in the world around you. But otherwise, the only other possible reaction from this, I'm going to add one more, just because you've seen this already. And this isn't the only other, it's just the only other one that I'm going to show you, just because you've seen it. Hopefully you remember that nicotine example from your test, from your last test that you did. Nicotine has carbon, hydrogen, and nitrogen, so when it burns, you actually get slightly different products, right? Again, the carbon with oxygen is still going to make carbon dioxide. The hydrogen with oxygen is still going to make water. But then I'm going to get one more possible product here. Nitrogen with oxygen would make something like this nitrogen dioxide. And again, unless I know what X, Y, and Z are, I'm not going to be able to balance this. Remember, you actually, on the test, did this backwards. You figured out what numbers went in front of carbon dioxide, water, and nitrogen dioxide to figure out what X, Y, and Z are. So again, I can't really balance this right now, but just so you can see, sometimes you can make other products besides carbon dioxide and water. You might make a nitrogen dioxide. You could also burn sulfur. You can burn phosphorus. You can burn a lot of different things that can be found in organic materials. So there could be other possible products. This is just one that we've seen before. Otherwise, one last thing to look at. If you look at these last 2 examples that I gave you, you should notice that they might actually fall under another category in our types of reactions, because I'm only making one product here and here. So again, not everything is separate and different, right? If I go backwards, or excuse me, this is not on there anymore, so you'd have to look at your own notes, right? If you look at your synthesis reactions, we might have used these 2 examples before, right? I'm only making one product, so technically it's also a synthesis, but these are definitely combustion reactions too, because of all that energy that's being produced. That's what makes a combustion reaction different, for sure. So more accurately, you would call these things combustion reactions, but they are technically also synthesis reactions. Otherwise, that's everything from the notes.